All right, so once again, we've got an equation. And, on the calculator, you can always graph the left, graph the right, see where they intersect. But these are set up on this topic so that you can do it by hand. Here, I know it doesn't look like it at first. Now, there's more than one way to tackle this thing without starting with the calculator. But the method that they're hoping that we'll employ is to say, all right, let's rewrite one or both bases of the exponents so that they are the same. Well, I can't do anything with 2. It's prime. I can't break it down. But 32 is the same thing as 2 to the 5th, and we've seen that in other instances. And so, let's see, yeah, write it down correctly. And so, with a power raised to a power, powers multiply. So I get 35 minus 20x. Now, at this point, the bases are the same. Well, if that's true, which clearly it is, and the left side and the right side equation are actually equal, which says it is, okay, then the only possible logical conclusion we can come to at this point is that the exponents are the same. Because if they're different, well, the left and right sides aren't going to match up. So with the bases of the exponents the same, we can just say, well, the exponents are the same. And we set them equal to each other. We've got that. Then we can say, oh, yeah, I know how to solve these. Yeah. Let's add 20x to both sides. Get that. And then I'll subtract 35 from both sides. And get that, 45. And now I can run it through the quadratic formula, or completing the square, or this will factor actually. So I'll just do x minus 5, x minus 9. It's factored. I set each factor equal to 0. And I get 5 and 9 for my answers. And that's how it's done. So you just have to rewrite the bases of the exponents so that they are the same. So for example, on this one, you would rewrite the 36 as 6 squared. Okay. And on this one, you could rewrite 16 as 4 squared. Or if you want to be cute, you could say 4 is 2 squared and 16 is 2 to the 4th, and then they both have a base of 2, but that would be a little more work than is required. All right, so on this one, solving for the variable, no big deal. It's stuck in an exponent. So, if you've got an exponential form of an equation or logarithmic form and you can't solve, shift to the other form. So log base 4 of 7 equals negative 5y, which is now quite a bit easier. So if I divide by negative 5, I get that. And let's see, that's going to be, it says go to the nearest hundredth, so it wants us to plug it in. Now, if it said in the instructions, instead of decimal answer, if it said exact answer would mean stop right there. Okay, it would mean go right there. That's the exact answer, because if I plug it into a calculator, it's only going to give me accuracy to like 9 decimal places, which is great, but not exact. So if it were exact, which you'll see that on another topic, this is where you stop. Okay, so I'm just not even going to do that topic, because essentially I just did by saying that. All right, so let's plug this thing into the calculator to get some accuracy here. So I'm going to make a fraction, and then I'll make a log. And let's see, 4, 7 over negative 5. And there's our answer, negative 0.28. Accurate to 2 decimal places. Okay. And that's it. You know what? I am going to do this one, even though it's exact answers, and I talked about it, because it's a little different. and the approach is going to be different. So there's more than one way to tackle this by hand. The way I'm going to do it is, well, the way they suggest. They say either do log base 10 or log base e. It doesn't matter as long as you do the same thing to both sides. Now remember, in an equation, you can do whatever you want as long as you do it to both sides. You can add 2 to both sides, divide both sides by 3, whatever. But you can also say, well, I'll do log base 10 of both sides. Well, if that and that are equal, then the log of this and the log of this will be equal. Okay, cool. Now, how could that possibly help? Looks like that makes things worse. Well, I can pull the exponents out using one of the log rules. Oops. Okay, and so we've got that. Cool, so the x's are now out of the exponents. We've got one inside the parentheses. Well, we know how to handle that. That's no problem. So we'll just deal with that right now. So negative x log 13 plus 5 log 13. Just multiply the log 13 through those parentheses. Okay, so x is out of the exponent. It's out of the parentheses, but it still appears in more than one place. So let's get the terms that contain x together. So I'm going to add x log 13 to both sides. Okay. So that I end up with 5 log 13 equals 10x log 5 plus x log 13. Okay, so I think that we can all agree, at least intuitively, that that's a step in the right direction, but we might not quite see, exactly why that's the case. Before we continue, bear in mind, this is just a number right here. It's a messy number, it's irrational, but it's just a single number. You can plug it in your calculator and get an answer. Okay, same thing with 10 times log base 5. Same thing with just log 13. Those are all just numbers, but they're kind of messy, so we leave them in this form because we want the exact answer. So we got the x out of the exponent. We got it out of the parentheses. We've got the we got the x's on the same side of the equation and everything else on the other. Now what? Well, now we factor out an x, and then that will make it so that there is only one x in the problem, which is what we want. We also want to solve for it. Okay, so we factored out the x. Now we're down to a single x. That's awesome. So now what? Well, remember, this is all one big number multiplied by x. So let's just divide both sides by that number. And then I don't know if I have enough room to write it out. So I'll just say divide both sides by it. Okay. Now on the left side, we get 5. Whoops. We get 5. Dang. My stylus is dying on me because I'm using it so much. 10 log 5 plus log. Yeah, the stylus is dying. Okay, equals x, and then this is the final answer. And of course, you could just plug this into your calculator. I think I'll just do that. What the heck? Let me do some erasing first. Now, in order to see if that, to double check that really is the solution, I got to plug it in for x into the original equation. That's kind of a big thing to plug in. So let's do this. Let's plug it in on this screen. Okay. you know what? I didn't really need that. This is all log base 10. So I can just use the log base 10 button right there, just to make my life a little easier. Okay. So that's our answer right there. Now, if I take that and I store that as, say, A, which you won't normally do this, but if I store that as A, now anytime I use the letter A, it's that number. Okay. So if I plug in the equation, the left side y1, right side y2, 13 to the negative x plus 5 to the negative x plus 5. And the left side was 5 to the 10x. Okay. And if I see, I'm going to go second window. I'm going to pick ask. That way I can plug in whatever I want on the table. And then I can just say, all right, I'm going to plug in A. All right. I could type this whole thing out right there, but it's kind of tricky because I can't use a fancy fraction. Now look at that. Okay. I plug that in and it makes the left side and the right side of the equation match. So everything's okay. Yeah, they're off ever so slightly after a few decimal places. That's just because of round off error. Nothing to worry about. If I were to type in the exact answer, so 5, let's see, log 13. Okay, and then I got to put parentheses around the numerator and denominator so that, you know, because the order of operations. 5. This is hard to read. Let's see. Let's log 13. And then an extra parenthesis so it's around the everything. Okay. Now I've typed it in exactly, and you'll notice, oh, it's okay. Well, still has a little round off error in there. All right. But it is the answer. Okay. If I were to go to the graph, okay, I could say second trace 5 to find the intersection point. Enter, enter, enter. There it is right there. Okay. But you got to do it by hand if you want the exact answer, because this is not going to cut the mustard. All right, on this one, you buy a laptop for $1,800, and guess what? The value drops. Of course it does. It's out of date as soon as you buy it. Okay, and it drops 70% every year. Whoa. That's terrible, but that's the life, the world we live in. After how many years will the laptop be worth $400? Okay, so the percent change, not the dollar change, but the percent change is constant each year. Therefore, this is going to be exponential, not linear. Okay, so our starting amount A is 1,800. And we, out of that 100%, we are losing 70% each year. All right, so you can just say, you know, if you want 1,800 times 0.3 to the t. That's totally cool. So you lose 70%. That means you end up with 30%. And we want to know when, let's do it like this, when the final amount is going to be $400. You know, we can get a decent idea about that, but just estimating. But, okay, so how are we going to do that? Well, we could divide both sides by 1,800 so that we get, if you do that, 400 divided by 1,800 is 2/9. And now we could convert to log form. Log base 0.3 of 2/9 is t. Okay. So let's go to the calculator. And we'll say alpha window 5.3 of 2 ninths. And we get 1.25 years. Let's see, it said, write the smallest possible whole number. So 1 year. Okay, it's actually 1.25 years, but they want just a whole number, so no decimal. So 1 year would be the answer. Wow, that's terrible. Buy it at 1,800. A year later, it's only worth 400. Now, another way to do it would be to, and this is worth seeing, be to say, all right, let's take that original equation we had, or the original function, 1,800 times 0.3 raised to the x power, the time, whatever. Okay, and if I go to the table, I want to know, when does this thing get down to the $400 value? Oh, wait a minute. I gotta go second window. Let's go there. Let's start off at year 0. So at year 1, we're down to $540 of value. At year 2, we're down to 162. So yeah, somewhere between year 1 and year 2. In fact, exactly 1.25. So that is, how we would do it. All right, so an initial amount of $2,100 is invested in an account, an interest rate of 5% per year, compounded continuously. And continuously is the key word. So when you are doing compound interest, normally you use this formula right here, which we have seen. But that's when interest is compounded like daily, so n is 365, or monthly, so n is 12, or semi-annually, so n is 2. But if it's continuously, well, what would n equal? Well, then that means you need a new formula, because, yeah, a equals PERT. Okay, once again, P is the original amount, A is the final amount of whatever you're counting, in this case, money. And R is still the interest rate. T is still time, measured in years. And E is just that irrational number that's approximately 2.7. Okay, so it says you start with 2,100. Cool, so that's our P. At an interest rate of 0.05. Okay, and it says find the amount of in the account after 2 years. Okay, cool. Let's check it out real quick here. Okay, so we'll go 2,100. Whoops. And then E, so second ln will be E to the 0.05 times 2. And so we're going to have $2,320.86. I guess I could write that down. $2,320.86. Okay. And that's all we do there. All right, so suppose that $3,000 is initially invested in an account at a fixed interest rate compounded continuously. So I see continuously, so I'm thinking, this looks like a job for PERT. Okay. So 3,000 is initially invested, so that's my principal. At some fixed interest rate, we're going to end up with 32.66. So this isn't going to be probably happening for very long. Well, yeah, this is going on for 2 years. Then the question is, what's the interest rate? Okay. So we got to divide both sides by 3,000, and we're not going to do any intermediate computations because that will lead to round off error. So 32.66 over 3,000, or could, usually it does. That's an E, by the way, just in case you couldn't tell. All right, now it's just the base of the exponent, and the other side of the equation. So I can convert to log form. So log base E of 3266 over 3000 equals 2R. Divide both sides by 2. And there's the answer. If we wanted just exact answer, but nobody's going to use that in finance, so let's not. Okay, let's go to the calculator and plug this in and see what we get. Okay, so we're going to go ln of 3266 over 3000, and then we will divide all that by 2. And it looks like, let's see, what did they say? Okay, nearest hundredth. So if we write this as a percent, the decimal point winds up between the 4 and the 2. So 4.25% would be the answer. 4.25%, 4.25%. Yeah, that's all I got.